Okay, good morning, everyone. Welcome to the fourth edition of the Next Gen Road Fuels webinar series. For those of you who have joined our previous webinars, you would have heard about the economics and also feedstocks and other research at the front end of this process. Now, today we're going to hear from Catherine, Ellie and Andreas about how we can actually use this biocrude to be upgraded to be actually used as a functioning fuel. So just a couple of housekeeping things before I pass over to Catherine for your introduction. If you want to ask a question, please do, but please write it in the questions and answer box, not the chat box. The chat box is for any technical issues. All questions will be answered either at the end of the presentation, or if we have too many questions, your answer will be written to you either in the box or in an email following. Okay, so off to Catherine. Thank you very much.
Thank you, Emma. I am going to share my screen. Please let me know when you can see it.
Perfect.
Okay, good. So thank you, Emma, for the introduction. As you mentioned, I am going to give a short recap of the Next Generation Road Fuel Project roadmap. I will follow with an overview of the biocrude characterization and the upgrading approach target in the project. I will finalize this part of the presentation with mentioning the project next steps. The project targets the identification and development of pathways for better utilization of multiple urban waste streams, such as sewage, sludge, organic waste, and construction good waste. Through the project, we have demonstrated already that it's possible to convert these streams into biocrude via hydrothermal liquefaction, and that is possible to produce raw materials for fertilizers and proteins, thus fostering the urban transition towards circular economy. However, could the biocrude produced from this feedstock be used as a fuel? Could this biocrude be upgraded and power a truck? Those answers to these questions are going to be done by the consortium. And for that, the consortium put together 4 technology and knowledge providers for biocrude upgrading and characterization. This team includes the participation of CPIRI, Technical University of Munich, ENI, Haldor Topsoe, and Steeper Energy. From the different feedstock tested on this project, we will dedicate this webinar to the HDL oil produced from sewage sludge. So let's start by looking at the biocrude most relevant characterization. The sewage sludge derived HDL oil is a petroleum-like oil. It has high heating value compared to other renewable oils. It has low viscosity. It is fluidic at 25 degrees Celsius. And the heteroatom content is within the range of other nitrogenate HDL feedstocks. The simulated distillation indicates that 28% of the biocrude corresponds to the boiling point distribution of diesel, and that 64% corresponds to the marine fuel range. Although this oil in many ways resembles its fossil counterparts, it has distinct properties that needs to be addressed during upgrading process. For instance, high ash content and heteroatom content. For these properties, can lead to operational problems such as, and just to mention some of them, catalyst fouling due to inorganic material deposition or accumulation in the surface of the catalyst that may end on catalyst deactivation. Another one can be reactor temperature control due to the high exothermic reactions during biocrude deoxygenation and stabilization. And to mention another one, recycling of the upgraded and partial upgraded oil. This is a common practice in the refineries, but we know that can lead to potential clogging problems due to the reduction of incompatibility or due to the reduction of compatibility between the biocrude and the hydrotreated oil. So if we look at the ash content, how we can improve this? This ash content can be improved by either doing further demineralization at the HDL facility or by a garbage test. The heteroatom content can be reduced by hydroprocessing, and the total acid number, which is mainly due to the presence of carboxylic acids, can be reduced by hydrogenation as well. In conclusion, similar to other HDL oils and fossil counterparts, this oil needs to be upgraded to be used as a finished fuels. As part of the next generation road fuel project, we have developed a modular upgrading pathway combining electrocatalytic and hydroprocessing stages to produce renewable fuel from this sewage-derived HDL oil. Details on the electrocatalytic hydrogenation stage will be provided by Andy, and Ellie is going to give us an overview of the thermal catalytic hydrotreatment. Finally, I am going to present the most outstanding results that we have obtained in continuous hydrotreating stages of this oil. What is coming, or what is upcoming stages of activities in the project? We are going to be doing engine test. The project is taking two approaches. One scenario is the utilization of this biocrude as a fuel, doing minimum upgrading, and the other is to use the hydrotreated fraction as an oil. I will not provide further details because I hope to have another webinar that is going to focus just on the engine test. This ends the first part of my presentation. Thank you.
So, welcome from Munich side. I would like to talk today about our concepts of coupling electrochemical conversion to catalysis. So we are working on the first step in this procedure, and we try to convert the first part of the biocrude, but at the same time also to produce some hydrogen then for the later stage of the process with the more or less the catalytic process. So what is our motivation to do that? And the motivation essentially is to see what the differences and the similarities, and the more the similarities of hydrogen produced either by absorbing hydrogen from the gas phase compared to hydrogen produced by electrocatalytic processes. And as the hydrogen then is the reacting agent for hydrogenation, it shouldn't make a difference because only chemical potential of hydrogen on the surface describes how fast the reaction is going to happen. Doesn't matter how we're getting the hydrogen. But getting the hydrogen via electrocatalytic processes obviously is much more environmentally friendly, and it gives us the chances also to do reactions in liquid phase. And what we see, and we will do some fundamental research, is how, for instance, concentration of reactants will influence the reactivity on the surface. So we're doing very fundamental studies in this type of cell. So we're having a two-cell compartment, one where's the catalyst in, where we do the reduction. We are producing the protons out of electrocatalytic processes. The protons go through a membrane, and of course we are balancing the charge here by doing oxygen on the other side. And we use currently model substances. So we do model substances having the chemical functionality similar to the biocrude, but being more defined. And we would like to do defined catalysis on defined reactivity inside this electrocatalytic cell. So as I told you, we're looking at the similarities. So what are the similarities? We can either do hydrogen from the gas phase, and hydrogen from the gas phase, when hydrogen absorbs on a metal side, it produces some hydrogen on the surface. So this is more or less what you see on this side here. On the other side, we can get hydrogen out of the aqueous phase. We do electron transfer, and we form a hydrogen atom on the surface. And now the question is this hydrogen atom the same? And what are the differences between this hydrogen atom with respect to its reactivity? So does this hydrogen have the same reactivity on the surface if it comes from the gas phase via external hydrogen pressure, or we are producing the hydrogen via the electrocatalytic process? And you see that here on this slide. So this is essentially the key to our working hypothesis. So if the hydrogen comes from the gas phase, we can hydrogenate. If the hydrogen comes from the aqueous phase with electron transfer, we have hydrogen on the surface. And now this hydrogen, the question is this the same or is it different? So we're looking into different concepts, and first we would like to look at the hydrogen itself. So hydrogen itself, is there a difference if it sorbs from the gas phase or it sorbs in an aqueous phase? And there is a difference. And you know, if you have hydrogen on a metal surface, even at room temperature, you get a full coverage of hydrogen on a single metal, on a defined metal surface. So hydrogen adsorption fully covers all metal sites. If you do the same in aqueous phase, we see here on single crystal, but also on a zeolite, you see that we're having significantly lower coverage. So the binding of hydrogen is significantly weaker inside the aqueous phase than in for the gas phase. So hydrogen is weaker bound to the surface, but it's bound to the surface. So even if we put hydrogen on top of the gas phase, hydrogen is being going into the phase, over the phase boundary, into the liquid phase, and then dissociates on the surface. And we're forming dissociated hydrogen atoms on the surface, same type as we're getting them from electrocatalysis. So let's look a little bit into the reactivity. And for the reactivity studies, we use the following configuration. I showed you that we're having a cell which has essentially an anodic part, a membrane, and on the cathodic side, we use very often a biphasic operation. And having a biphasic operation, we use that because some of these substances will not be soluble in water only. So very poor solubility in water, they will be essentially solved in organic phase. And we know we do the reaction, obviously the hydrogen is only produced in the aqueous phase. Because here in the aqueous phase, we have protons, the electrons reduce the protons, and we're forming some hydrogen on the surface. So only in the aqueous phase the reaction is going to happen, but we will have the hydrogen, the reactant form adsorbed or mainly present in the organic phase. And now we can see how the reactivity changes. And we see that the reactivity changes as function of the solubility. Of course, if we have a very good solubility, like we use ethyl acetate for the aqueous phase, for the organic phase, we see that all reactant is in the organic phase. So these blue dots are the reactant in the organic phase. The orange dots, which are down to 0, is essentially the reactant in the aqueous phase. We do cresol hydrogenation towards the ketone and towards the alcohol. And you see, of course, if the hydrogen is produced in the aqueous phase, and essentially there's no concentration of the reactant in the aqueous phase, we see a very poor reactivity. Then we can go to another solvent, and if the other solvent is benzene, organic benzene, we see that some of the reactant now goes already into the aqueous phase, but we see that benzene blocks most of the sites, so we don't see any reactivity towards any products, because also we're having a larger concentration now in the organic phase, we don't see actually any conversion. Then you see you do a poorly a solvent where most of the reactant or model substance is in the organic phase and the aqueous phase. Now we see we have more in the aqueous phase, and as soon as we have more in the aqueous phase, you see that the product is being formed, and we see that the product goes into the aqueous phase, but also in the organic phase. So essentially, as soon as some product is being formed, we extract it back into the organic phase, because the solubility of the product in the organic phase is higher than in the aqueous phase. So playing with the solubility, playing with the concentrations, we can use even a non-water soluble or poorly water soluble reactants, and we can carry out the reaction. At the same time, we're producing the hydrogen. So it's not all reaction goes towards the organic phase, but also some hydrogen is being produced. And this hydrogen then can be used in the later stage, the next stage, which will be described by Eli. So let's look at the summary. What I would like to give on our research is that it depends on the solubility, and the lower the solubility, the higher the rate. So you have to have a certain solubility to solve it, but then we need, as the reactivity or the reaction happens essentially in the liquid phase, there we need that we have a concentration of the reactant inside the liquid phase, because in the liquid phase we have the proton, in the aqueous phase we have the protons, and this proton is going to be reduced to hydrogen, and this hydrogen is then used for hydrogenation reactions. And currently we're comparing the rates for this electrocatalytic reaction towards reactions where we add additionally hydrogen. And we see very similar kinetics, but this is still too early to talk about. So hydrogen, essentially, this is the main message of our work. There is not a difference on the hydrogen. The hydrogen on the metal, independent if it comes via absorption process from the gas phase and followed up by dissociation, or by electroreduction from the aqueous phase, behaves pretty much the same. So the hydrogen is the same, and the reactivity is the same. And with this, I would like to finish my presentation and give back to Ellie now to talk about the next step.
Thank you, Andy. So just let me share my screen. So good morning also from Thessaloniki, Greece. My name is Elira Kleus and I come from the Chemical Process and Energy Resources Institute here in Thessaloniki. And as you already heard, we have been working on the upgrading of the HTL oil. Katerina gave a very good introduction of the overall concept of the upgrading that we have been following in the NextGen road project. So this combined electrothermal catalytic hydrotreating. You've already heard a nice presentation from Andy on the electrocatalytic part. So our part, our CPRI, has been focused on the second thermal catalytic hydrotreating step, where the partially upgraded HTL oil, conceptually coming from the electrocatalytic hydrogenation, together with additional hydrogen produced in the first step, goes into a thermal catalytic hydrotreating process, where at more severe hydrotreating conditions, we fully upgrade the oil and into a high quality fuel that meets fuel specifications. So I will talk to you about the work that we've done on this step, and I will focus my talk on the new catalyst that we have been trying to develop in order to upgrade the HTL oil. So Katerina already also gave you a very good introduction on the challenges that are associated with the HTL oil upgrading, and which are basically connected to the properties of the oil itself, especially in the case of hydrothermal liquefaction oil coming from waste and sewage sludge. It's an oil that has high inorganic content, it has high oxygen, but also nitrogen content coming from the proteins in the waste, acidity, viscosity, also a high coke forming tendency. And all these properties bring their own issues and challenges in the hydrotreating of this oil. So typical hydrotreating catalysts have not been designed and developed to work with such high inorganics, so they tend to deactivate. Also, the nitrogen containing compounds are very resilient, and therefore they require severe hydrotreating conditions, high temperatures, that in turn also lead to issues associated with coking, reactor clogging, and different other unwanted side effects. So I've talked about the typical hydrotreating catalyst. Typically, a hydrotreatment is a classical refinery process. All refineries have a hydrotreater, and the catalysts are usually nickel molybdenum or cobaltium molybdenum sulfide supported on alumina. So these are very active catalytic materials. However, they have been developed for fossil-based feedstocks that have different properties. So when we try to use this commercial catalyst with renewable fuels, such as the HTL, we get problems, as I already said, with catalyst deactivation. And this is here just an example, a figure from a very nice publication by D.C. Elliott of PNNL, and they have done a lot of work on upgrading of renewable fuels, where we can see that how a commercial catalyst deactivates in the upgrading of lignocellulosic HTL oil, and you can see that even in 40 hours time on stream, it loses its deoxygenation activity. So this basically gives birth to the need of the development of new catalysts that are more suited for the upgrading of such fuels with the properties that they have when they come from other feedstocks such as waste. So from literature and from own previous work, we've seen that nickel and molybdenum-based nitrites, carbides, and phosphides do exhibit a promising behavior for the hydrotreatment of pyrolysis oils coming from catalytic fast biomass pyrolysis, but also hydrothermal liquefaction. And just as an example, this is a graphical abstract from a previous work of our group with the group of Ferdi Schuth at Max Planck Institute in Germany, where we worked on nickel phosphide and molybdenum carbide catalysts, and were able at very mild conditions, so at very low hydrogen pressure, to upgrade pyrolysis oil coming from lignocellulosic biomass. And with this catalyst, we managed to get a very good upgrading into hydrocarbons, so fuels, and also valuable chemicals, these alkyl phenols. This is also an example from literature from an older work of Teroyama, where they were trying to remove nitrogen from gas oil derived from the liquefaction of coal. So they've tried different molybdenum carbides, sulfides, and nitrites compared to commercial NEMO catalyst. And you can see here the hydrodenitrogenation degree, where it is apparent that the molybdenum nitrite gives the highest removal of nitrogen. So inspired by our previous work and literature, during the project, we tried to develop a series of molybdenum nitrite-based catalysts for the hydrotreatment of the HTL oil. So we synthesized a series of catalysts with a constant loading in molybdenum nitride around 11%, and supported them on different types of oxide carriers such as zirconium, cerium oxide, SBA15, MCM41, and also activated carbon. So here in the slide, you can see the synthesis procedure that we followed. So basically with a classical wet impregnation, we prepared the molybdenum oxide respective catalysts on these different supports. And after we calcined them, we followed a strict temperature program, nitridation program in 16% hydrogen nitrogen gas phase, and treated them up to 700 degrees, basically to convert the molybdenum oxide phase into the desired molybdenum nitrite phase. As these materials are pyrophoric, we also, at the end, before exposing them to air, did a mild passivation step at room temperature with a low oxygen concentration. We also characterize these materials in order to determine their basic physicochemical properties. Here you can see some results related to the textural properties of our catalyst, so the BET surface area, pore volume, and average pore diameter. So we characterize the pure supports, the oxidic phase of the catalyst, and also the final, of course, nitrite-based phase. And we also prepared an unsupported material as a benchmark. So we can see that the unsupported molybdenum nitrite phase has a very low surface area. Basically, it's non-porous and it just has external surface area, as also seen by this nitrogen absorption-desorption isotherms. When we put this on a support, then we get a wide variation of different surface areas, basically depending on the initial surface area of the support. And as an example, we got a material, a catalyst with very low surface area, 30 for the nitrite supported on cerium oxide, and very high surface area catalyst, for example, the molybdenum nitrite on NCM41, around 700 square meters per gram. Also on activated carbon, we get a very high surface area of around 800. Besides textural properties, we also did X-ray diffraction to see what kind of crystal phases form on the materials. These are the XRD diffractograms of the catalysts before nitridation, so in oxide form. If we look at the bulk material, we have the characteristic diffractions of molybdenum trioxide. Whereas in the case of the catalyst supported on carbon, ceria, and zirconia, we only get diffraction lines corresponding to the supports, suggesting that the molybdenum oxide phase is highly dispersed on the surface of the catalysts. On the two silica-based supports, SBA and MCM41, we do get some diffractions related to the molybdenum oxide phase. We then repeated this characterization for the catalysts in the nitrite form. Again, if we look at the bulk material, we see now diffractions corresponding to the molybdenum nitrite phase, suggesting that we have successful conversion of molybdenum oxide to molybdenum nitrite. This was not 100% complete, as we also got some diffractions attributed to molybdenum dioxide and the molybdenum metal. When we go to the supported catalysts, again, in the case of carbon, ceria, and zirconia, we see no diffractions attributed to the nitrite phase, only in the case of the SBA and MCM41, suggesting changes basically in the dispersion of the active phase, depending on the nature of the support. To investigate this further, we also determined the dispersion of molybdenum nitrite by hydrogen chemisorption. So we sorbed hydrogen on the surface at 250, and we then increased the temperature under helium to do a temperature programmed desorption of this chemisorped hydrogen. Here in the figure, you can see the evolution of hydrogen as a function of temperature for the different materials. We see significant changes, both related to the temperature of desorption of hydrogen, but also the amount of desorbed hydrogen, depending on the different supports that we use to prepare the catalyst. In all cases, however, we see two major hydrogen desorption peaks, one around 350 to 450 degrees Celsius, and one at higher temperature, 7 to 750 degrees Celsius. And we know from literature that in this type of catalyst, the interaction of hydrogen occurs on coordinatively unsaturated molybdenum sites, so nitrogen deficient molybdenum sites where hydrogen dissociates heterolytically to generate molybdenum hydrogen and nitrogen hydrogen moieties. So we also quantified these peaks in order to see how much is the hydrogen that is dissolved. And you can see here for each catalyst the amount of hydrogen dissolved in moles per gram, but also normalized per mole of molybdenum. And if we focus on this column here on the normalized result, we can see that the use of the support increases considerably the dispersion of molybdenum compared to the bulk material. The bulk material has a hydrogen desorption of about 0.03 moles per mole of molybdenum, whereas this increases with the use of support and reaches its highest value on the high surface area MCM41 support, where we have a desorption of hydrogen equal to 0.5 moles of hydrogen per mole of molybdenum. We then move forward to evaluate the catalytic performance of these materials and to do a catalyst screening. And we did this in small scale batch reactors that we have available here in the lab. For this screening test, we did not work directly with the real HTL oil. HTL oil is a very complex feedstock. It consists of more than 10,000 compounds. So it's really difficult to do screening when you have such a complex feed. So in order to evaluate the catalytic performance of the material, we did this using model compounds, which are representative of compounds existing in the HTL oil. And we selected three representative model compounds: an oxygenated one, a p-cresol that you see here on the slide, a heterocyclic nitrogen-containing compound such as pyridine, and also an octanamide, as we also saw a high concentration of amides in the original HTL oil. For all these tests, we use standard operating conditions. So we did all the tests at 350 degrees Celsius, 60 bars of hydrogen, a catalyst to feed ratio of 0.05, so 5 weight %, and a reaction time of 4 hours. So I will start with the results pertaining to the hydrogenation of p-cresol. Just to put this into context, I'm showing here the possible reaction pathways in the hydrodeoxygenation of p-cresol. So there are two dominant reaction routes. The one is the alicyclic hydrogenation, dehydrogenation route, where basically the reaction proceeds by pre-hydrogenation of the aromatic ring. And then we have the removal of the hydroxyl group, leading to the formation of different cycloalkenes and cycloalkanes. The other route is the direct deoxygenation, which involves first the breaking of the carbon-oxygen bonds to obtain aromatics. And then we have formation of toluene, benzene, and xylenes, therefore removing the oxygen without hydrogenating the ring. And this would be a desirable route due to the, of course, high value of aromatics, but also due to the fact that we have a low hydrogen consumption. Hydrogen is an important resource, so we would also like to minimize the consumption of hydrogen. And saying that, I'm showing here the results that we got for the hydrogenation of p-cresol over the supported molybdenum nitrite catalysts, and also over a commercial classical nickel molybdenum catalyst for comparison. What I'm showing here in this graph is the conversion of p-cresol with the black color, and I'm also showing the yields to the different products that we got during these tests. So we can see that in general, we have a very high conversion of p-cresol over all materials except for the nitrite supported on Syria and MCM 41, which is good news. So they're all active in removing oxygen. However, we do have a difference in the product distribution. Dominant product is in most cases toluene, so an aromatic compound, but we also get, for example, 4-methyl cyclohexanol and also cyclohexane and cyclohexene resulting from the hydrogenation of the ring. So by comparing these results, we can see that the bulk, the unsupported molybdenum nitride, appears superior to the supported catalyst, but also to the commercial nickel molybdenum catalyst, as it managed to remove oxygen and giving the highest yield to toluene, so without hydrogenating the aromatic ring, and therefore with a low hydrogen consumption, which, as I said, is desirable. We then proceeded to the test with pyridine, a heterocyclic nitrogen-containing compound. Again, here you can see the classical reaction pathway. So hydrogen hydrogenates the aromatic ring of pyridine, forming pyridine. Then we have a ring opening to pentylamine, which is then decomposed to pentane and ammonium. In this graph here, I'm showing the conversion of pyridine over the different catalysts and also the amount of pyridine in the feed and in the liquid product that we got from the reaction. I should say that the main reaction product over all catalytic materials was nipentane, with only a small production of C1 to C3 alkanes. If we look at the conversion, we achieved full conversion in the case of the commercial NEMO catalyst and the catalyst supported on carbon. In all other cases, the removal, the conversion of pyridine was something in the range of 70 to about 85%. So we're thinking whether there is some connection between this performance of the materials and their properties. And we saw that the pyridine conversion follows the surface area of the materials. You can see here I'm plotting the surface area of the catalyst as a function, the pyridine conversion as a function of the surface area. And we can see a pretty good correlation suggesting that the higher the surface area, the better the dispersion of molybdenum nitride, and therefore this leads to a higher number of active sites that catalyze the reaction. We also measured with elemental analysis the amount of nitrogen in the liquid product of the reaction over the different catalytic materials, and we calculated the HDN degree, so the hydrodenitроgenation degree. And you can see here that the only catalyst basically that achieved 100% or almost 100% removal of nitrogen was the commercial nickel molybdenum catalyst. So although we saw a better behavior of the nitrites in removing oxygen, we got a better performance from the commercial catalysts in the removal of nitrogen. And as in the case of the HTL switch sludge oil, nitrogen is more of an issue. We decided to perform the rest of our tests with the commercial material that we also tested in the hydrogenation of octanamide in oleic acid. And I'm just showing here the performance of the material in terms of oxygen content removal and nitrogen removal. And we can see that even when we have nitrogen and oxygen together in a compound, the commercial NEMO catalyst still performs very well in removing both oxygen and nitrogen, to a very high extent. So we did all this work that I presented in the first steps of the project, and then moving on, we started working with the real switch sludge derived HTL oil that we received from our partners in Denmark. We did a lot of tests in the small scale unit in order to investigate the reactor conditions and also the optimum hydrotreatment configuration. From all these tests, I don't have time to show the details, but we concluded that the best upgrade, the most successful upgrading is achieved when we have a two-stage hydrotreatment process, when we have a first step to stabilize the oil at 250 degrees Celsius, and then a more severe hydrotreatment at 350, both done at mild relatively reaction pressure, so with 80 bar hydrogen. And I've just also copied here some characteristic results. From this work, we've seen that these are gasoline, diesel, and residue fractions in the feedstock, the intermediate stabilized oil, and the final upgraded oil, where we saw that in the final product, we have more than 70% components in the gasoline and diesel range, and at the same time, we managed to remove 75% of any sulfur and oxygen that was initially contained in the feed. Unfortunately, things were not so good in terms of nitrogen. Nitrogen, we have seen that it's very resilient, and at these conditions, at least, we still did not manage to get a very high nitrogen removal, which still remains a challenge for the HTL oil feedstock. At the moment, we are at the final months of the project, and it's time to demonstrate this process on larger scale. Katerina will show you the work that they have been doing at Steeper Energy, but we have also been running experiments in the CPRI pilot scale unit. So at the moment, we are running for over 100 hours time on stream the stabilization step of the HTL oil. The good thing about the pilot scale unit that we have here is that we are flexible in terms of the reactor type. So the unit is equipped both with a fixed bed reactor and with a slurry type reactor. The slurry type reactor is a reactor which is suitable for heavy feedstocks, such as the HTL oil. And we want to investigate whether by using the slurry type reactor, we can avoid having two hydrotreating steps, and we can do everything in one step. So as I said, we're currently running in the fixed bed reactor, and hopefully we will soon have results to share with a slurry reactor. And with this, I would like to conclude. I think I've taken Emma more time than I should. We have got a lot of experience on the updating of HTL oil during these years that we have been working in this project. So we saw that the upgrading of oil from difficult feeds such as municipal solid waste and sewage sludge requires careful catalyst development and catalyst selection, and also at the same time optimization of hydrotreating configuration and operating conditions. Molybdenum nitride-based catalysts do show a promising performance to remove oxygen. However, we need to optimize them further to achieve full deoxygenation, but at the same time also full denitrogenation. And we're also at the stage where we believe that the use of a slurry type reactor can overcome issues associated with caulking and reactor flagging that we see in fixed bed reactors, and that basically require a more multi-step process, whereas with the slurry type reactor, perhaps this can be done in one step. Okay, and I think that was all from me, and I will give the floor to Katerina to show you the very interesting work that they have done on their pilot scale.
Thank you, Ellie. I'm going to share my screen again. Can you see my screen now?
Yep.
Great. So thank you, Ellie and Andy, for those excellent presentation. Thank you, Ellie, for giving a very big and good overview of the Catalyst Challenge and what you guys have been doing on the CPIR. To conclude this webinar, I will present the most outstanding results from the continuous hydrotreating of this sewage sludge derived HTL oil. Those results has been obtained, as Ellie mentioned, in the Advanced Biofuel Center of Steeper Energy. Okay, so as I mentioned at the beginning of this webinar, we have demonstrated that HTL oil can be produced from multiple urban waste streams. However, for us at the Steeper Energy, it's not enough to just make the biocrude. We have to make sure this oil integrates into the existing petroleum value chain and demonstrate its pathways to production of finished transportation fuels. To do so, we are evaluating the uses of this biocrude as a heating oil or marine fuel through minimal upgrading. Alternative, the use of this as a diesel blend through partial upgrading or through co-processing at existing refineries. And finally, the study of the upgrading of this oil through our own standalone upgrading technologies for the production of marine, diesel, jet fuel, gasoline, and value-added chemicals. At the Steeper Energy, we target our R&D activities on upgrading and co-processing technologies in our Advanced Biofuel Center located in Alberta, in Calgary, Alberta, Canada. This center is a specialized laboratory focused on oil and upgrading product characterization and processes evaluation, including oil upgrading, hydrotreating, refining, co-processing with petroleum feedstocks, and blending on the end products with conventional fuels. Here, we are advancing in our knowledge of the hydrofraction oil, the products from upgrading, the stability of the oil, blending, and compatibility with petroleum feedstocks and fuels. We are demonstrating full refinery integration of the different biocrudes that are produced by steeper energy. And we are developing techno-economic pathways for the renewable fuels, all which enhance steeper upgrading and refinery co-processing capabilities. Based on the characterization of the biocrude that was presented through this webinar, the targets of the pathway that has been developed at the Steeper Advanced Biofuel Center targets the oil demineralization by the use of a garbet, heteroatom content reduction, tan elimination, microcarbon residue, maximization of the light fuels production, as well as maximization of the residue conversion. The biocrude upgrading pathway includes a garbet stage followed by a series of hydrotreating stages. The upgrading results presented on these slides were obtained by a combination of continuous hydrotreating stages using commercial sulfuric catalysts. Over 120 hours of continuous operation were achieved for each stage with reproducible results. The average closing of the liquid mass balance was above 94%. And in the results, we can see that a significant reduction of iron content was achieved during the garbet stage. So if we look at the product that we are calling here product from stage number 1, that is the product after the garbet stage. Although the target of this stage was only oil demineralization, we can see that there is a slight reduction on the oxygen content, sulfur content, and the microcarbon residue. In overall, after hydrotreating, there is a significant reduction of the boiling point and residue fraction. We can look at the this diagram. For example, after first stage of hydrotreating, which we call their product from stage 2, 58% of the residue conversion is achieved, and the drop in diesel fraction, which is the fraction that has a boiling point between 150 to 350 degrees Celsius, was doubled after hydrotreating stage. Finally, we can see that after a second hydrotreating stage, which if we look at the table is the product that we call product stage 3, we achieve a reduction of more than 90% of oxygen and sulfur. And nitrogen was able to be reduced from 4% to 2.8%, which is around 30% of reduction. We know that the nitrogen components are still resilient, as Ellie was mentioning. Further hydrotreating is required. However, we are currently doing blending tests to see how much it is possible to blend in the different fuels, such as diesel or marine fuel, by performing different stages of upgrading. To finalize, after the second stage of hydrotreatment, we can notice that the microcarbon residue was reduced in about 80%, so from 12 to 1.8 weight percentage, and the total acid number minimization was achieved. To conclude this presentation, we have demonstrated that sewage sludge derived HDL oil can be upgraded via conventional hydrotreating. 98% of the hydrogen removal was achieved after a garbet test, that the physical properties of the hydrofraction oil were significantly improved, and that 58% of the residue conversion was achieved, and that the drop in diesel fraction is doubled after the third hydrotreating stage. Currently, we are performing product characterization, blending tests with petroleum fuels, and we hope to give you a little bit of more in the details in publications and further presentations. Thank you for your attention, and I hope to be able to answer some of your questions in the Q&A session.
Thank you very much. It was a really interesting presentation from all of you. We just have two questions. One was asked during Andy's presentation about carbon footprint. Now, I'm not sure if that's something that Andy can answer, or maybe if you want to.
I can say something about that.
Okay.
That's not a problem. Well, the carbon footprint is essentially the amount of carbon dioxide produced out of the process. It's a very generous thing. If we discuss carbon footprint, obviously, with electrified processes, you have to discuss how you make the electricity. And the current technology is, of course, not all on renewable energy, electricity. So therefore, we have quite some carbon footprint by producing electricity, not out of the process itself. So if you make hydrogen on a traditional basis from steam reforming, you make a lot of carbon dioxide when you produce the hydrogen out of methane. So the process itself doesn't have any carbon footprint because we get the electricity. But the electricity production, of course, currently is related to carbon dioxide production as long as we rely on fossil fuels. And there is many discussion now going on in many countries how to change to more renewable energy. And currently in Germany, we have about 1/3 renewable and 2/3, half of it essentially from fossil fuels, and a very large fraction from coal. So Germany has a large fraction of electricity produced out of coal, and that's obviously causing some carbon footprint if you look for electrified processes. Electrified processes usually are targeted to reduce the carbon dioxide footprint, but this is, as I told you, heavily related to produce electricity by renewable sources like wind or solar energy.
Okay, thank you for that. I do know there's part of this project, there is a full environmental impact assessment being undertaken by one of the other work packages. Maybe that could be another webinar, we'll see, because we're running out of time, but definitely in the final conference, which will be held in October, there'll be some talk about the whole process, the whole, what can we say, cycle of the project. Okay, great, thank you for that. So Ellie, another question was asked during your presentation. I'll read it out to you. It is difficult to control the composition of the hydrocarbons in crude bio oil, especially from municipal solid waste. How would the reaction be controlled or modified such that hydrogeneration is possible?
Okay, so I don't know if the composition refers to the crude or the upgraded product. Anyway, as I said, the crude bio oil is obviously a very complex feedstock. It has many different thousands of compounds. So the idea in hydrogenation is to hydrotreat this and convert them to hydrocarbons. And once we do this, then we can easily do a normal distillation that is done in refineries in order to isolate, let's say, the different fractions, gasoline fraction, diesel fraction, marine fuel fraction, as Katerina already mentioned in her presentation. So, as I said, obviously they're a difficult feat, but once you manage to pass it through your hydrotreater, then it becomes simpler and more similar to what we are used to working with in oil refineries.
Great, thanks, Ellie. Next question is a general question. I'm not sure if we can answer this one or if it was answered in Gonzalo's, but it's I'll just read it out. So, considering the volume of oil obtained from the sewage sludge and the economics of the oil treatment for upgrade, is this process of great economic value? Does anyone want to ask Katerina?
If you don't mind, I can give just a brief. As you mentioned, yes, this was covered by Gonzalo's presentation, and this is going to be covered, of course, in the final report of the life cycle assessment of the oil. Whether it makes sense economically or not, it depends on what are the targets of the project, of the process. So we wanted to make sure that we give alternative for treatment of a challenge feedstock, such as the sewage sludge. And for giving an alternative treatment, then perhaps, yes, we are economical. However, to be able to use this oil, as a fuel, we have to do upgrading. And we know that removing of nitrogen is going to consume a considerable amount of nitrogen, of hydrogen. So economical value needs to be done after we finish the upgrading. So from the results that Ellie is going to present at the end of the project, for the results that Andy is going to present, I am sure that part of this hydrogen consumption can be covered by the technology that Andy was presenting on the electrocatalysis, and also by the use of the in situ hydrogen generation of the HTL process. So we have to evaluate different scenarios to be able to give an appropriate answer.
Great, thanks for that, Katerina. Yes, and as we mentioned before, there was a webinar 2, which covered some of the economics of the project. Of course, not completely because we haven't finished yet, but I can direct you to the Next Gen Road Fuels website if you want to watch that. Okay, great. Now I have another question here from Francesco Zimbaldi. Do you expect significant differences by using different feedstock to produce bio oils? How do you deal with that?
Ellie, am I viewing mine? And Ellie, if you want to go first, or?
Yeah. I mean,
Okay.
yeah, obviously, yes, we have significant differences depending on what kind of feedstock we use. So in the past, we have been mainly working, I mean, not us, scientific community, mainly working with biomass, lignocellulosic biomass. And in this case, we have high acidity, high water amount, high oxygen content. But as we are now switching also, so focus is also switching on wastes, things like municipal solid waste and sewage sludge that we have worked on in this project. Nitrogen, which hasn't been a problem before, so it's not there when you start from wood. And nitrogen is also not as important in the oil industry because, yeah, heavy crudes can have some nitrogen in, but nothing in the levels that you can find in oils coming from waste and proteins and algae and all that. So yes, and that's why we have been trying to see what type of catalyst would better work with this feedstock that comes from waste and has such a high nitrogen content. So dealing with it is by optimizing catalysts and optimizing conditions and upgrading configuration. It has been a challenge throughout this 3+ years of the project. But I think with Katerina, we have tried to move this forward much more than we were 3 years ago. So it can be done. It needs tuning, optimizing, catalyst development, all the things that I've already mentioned.
Exactly. Great. No, the research has come a long way in, well, it's a 4-year project, but all the research is already, and the bulk of it's already been done. So we can say 3 years of research and it's come a long way, but of course, more research is required. Completely. Okay, so there's more questions about costs and life cycle analysis. So I'll just direct you to the website where there's the recording of Gonzalo's webinar, and also to stay tuned because of course there'll be a final report that will summarize all of the research, which will include life cycle analysis. And for those of you who are mobile, there will be a final conference in October, which should be in Amsterdam. And we're hoping for it to be hybrid. So of course you can tune in as well. Oh, just one more question's come in. How can you see the perspective pilot to factory? I'm not sure how you can see. Would sorry, Katerina, would you just like to explain about your pilot site, maybe?
Yeah, Emma. So this is gonna go to complementing the Ellie's answer for the question before. So yes, we expect to have different qualities of the biocrude, depending on the feedstock that we are using on the HTL. The best oil, of course, or the ones that contains less heteroatom content is the oil that comes from forestry residue. The nitrogenate feedstocks, such as biopulp and sewage oil, are going to become a little bit of challenge, as Ellie was mentioning. And in terms of the pilot factory, I will say that at a steeper energy, and I can just speak for, for the hydrofaction technology, is we are currently on the commissioning of a demonstration unit in Tofte, Norway. That unit has a 30 barrels per day capacity, and the feedstock is mainly forestry residue. After that, we are gonna become commercial, hopefully, and the target is to have a pilot unit that has 2,000 barrels per day. Now, this is in the case of forestry residue. In the case of sewage sludge alone, the capacity of the unit needs to be lower because it's going to be depending on the availability of the feedstock. But of course, there is going to be aggregation of the different feedstocks and the different oil produced to be able to really concentrate these oils and have them upgraded either at a commercial refinery or in a standalone refinery.
Perfect, great. So I think we can say that there's a positive outlook for the future, and I think one day we will be making fuel from waste properly at a commercial level. So great, well, we've finished with the questions now. I think that's all of them. Oh, another question's just come in. Have you tried to use pyrolytic biochar and or other cheap materials as catalyst for HCl process? Now, I think this will be the final question. So have you tried using biochar in this? No, for this.
So not for the HCl process. Stipper's proprietary technology is called hydrofaction, and we use two homogeneous catalysts. If you guys want to get a little bit more deep into the technology, there is a paper that we published a few years ago that specify which catalyst we use. The paper title is Fundamentals of Hydrofaction. And the answer to that question is no, but in the process upgrading, perhaps Ellie, I don't know if you have used biochar as a support for any of your catalysts in CPIR. We haven't done that
We've done this for other processes where basically you use the biochar, you do the treatment and you convert it to activated carbon, and then you can deposit different metals on it. And it works, but we haven't tried specifically for this process. But just a general question on economics, because I see a lot of questions revolving around how can it be economically competitive to fossil fuels. And I say we are going through times where we see that this is so much based on the political situation, the overall situation. So if fossil fuels really go up, and we are now experiencing very, very expensive prices in fossil fuels, and therefore these things make renewable fuels much more competitive than they were in the past. And if this in combination with a strong policy to reduce CO2 emissions and go away from fossil fuels by carbon taxes or any other type of policies, then we shouldn't worry so much on economics, but rather to make it work to begin with. And yeah, if there is a will, there will be also a way for these things to be competitive in the market.
Precisely. Yes, I agree with that. Exactly. Okay, we just have 2 minutes left, and this Danny has asked this question, just the last question now, I promise. Is there any strategy to use transition heavy metals since the hydrogen to increase the productivity? So any strategy to use heavy metals, especially that some of them are fertile and release electrons?
Maybe it's 20, I guess.
No, we have not used more than rhodium. So rhodium, platinum, but what do you think about heavy metals?
Maybe some future research there.
Yeah, we have to define first what's a heavy metal. Okay,
so maybe Danny, maybe I can direct you to the our website, the Next Gen Road Fuels Project.
No. We have not used any radioactive elements.
Oh, okay.
Not allowed to use that, and don't think it's the way forward to use radioactive metals in catalytic reactions.
Great, excellent. So I hope everyone's enjoyed the presentation today. All the questions have been answered, but I do recommend, if you want to get in touch with us, I can direct you to either our LinkedIn profile or our website, which is nextgenroadfuelsproject.eu. And stay tuned. So hopefully there'll be another webinar at the beginning of the summer, which will talk about the engine testing, and again the final event, which will be held in October. Thank you very much, everyone. Have a nice day. Bye.